This one's working, right?
Yeah.
All right, so there's going to be 3 other speakers on different aspects of Bootstrap. So the next speaker is going to be Barak Gabai, who's going to be talking about matrix Bootstrap. All right, so take it away.
Okay. Is this on? Okay. Thanks, Shai. So I'm going to talk about matrix quantum mechanics Bootstrap, which is one example or one instance of using some technique that became popular over the last 8 years or so, and that is referred to often as matrix Bootstrap or lattice Bootstrap, depending on the context, but it's basically the same technique. And then I'm going to explain how to use it in finite temperature, which is a new development in the last 2 years. So first I'll review the methodology very quickly, then I'll move on to matrix quantum mechanics, and then to finite temperature, and I'll show you a little bit of plots. So it's all based on this paper, which hopefully will be out in the next week, with Minjae, Joshua, and Shi.
Well, what is that P?
Product placement. It's like the BBC product placement. So there are a lot of references by now on this subject. I'm not going to explain what each one of them is. That will take a third of the talk. But the first one in our field is by Anderson and Kuczynski in 2016, working kind of setting up the bootstrap problem for pure Yang-Mills on the lattice. Okay. So the first ingredient in any of these approaches, in any of these papers, is to find some positivity that your theory satisfies. So you need some notion of positivity. The simplest one, and the one that we'll need today, is this one, which is just the norm positivity of a Hilbert space for a quantum mechanical problem. But it can also be reflection positivity for the loops or for some statistical model on the lattice. And then the second ingredient you need is equations of motion. So the positivity, you can take your positivity constraint, you can make it into a matrix that have to be semi-definite positive, and you can put it into a semi-definite positive solver. But of course, the bounds you're going to get are not theory specific. So if you want to get your bounds to really converge to the theory you're interested in, you have to tell the solver which theory it is. And to do that, we include the equation of motion of the theory. So again, in our case, the simplest one is, or the simplest one which will be relevant to our case, is just that the commutate over the Hamiltonian is 0 in any stationary state. Okay. In the vacuum, definitely, and also in some finite temperature state. Okay. But it can be also loop equations or just equation of motion on a lattice. So we have these 2 constraints. That's the full set of constraints we're going to need to pin down our theory. But to make this tractable numerically, we're going to have to include also some rigorous truncation of the problem. So we're going to choose a subset of the variables, some subset of correlators, and then we're going to restrict only to the constraint that close within this subset. So that's why this is going to be a rigorous truncation. I'm not going to take a constraint where I have a sum of things and say, oh, this one is probably small, I'm going to just set it to 0. I'm going to strictly take only constraints that include only the variables that I restricted to. And so in our case, these variables are going to be this type of words up to a certain length. So this I would call length 7. This is also another word of length 7. And my truncation, if it's 8, I include this. If it's 6, I do not. Okay, so now, well, maybe the last thing I would say. So the setup goes this way. You write a code that writes a big semi-definite positive matrix that takes into account this positivity. Then you for the subset of variables that you chose, then you solve the equations of motions within that subset of variables. It decreases it all more to a smaller subset of variables, and then you just take the semi-definite positive matrix you have after substituting in the solution to the equation of motion and put it in an SDP solver. And it's the problem of some coder to make a good SDP solver, or a good physicist to make a good SDP solver. And okay, so now let's specify to matrix quantum mechanics. We're going to talk about the quantum mechanical system. This is standard quantum mechanical system, but with a lot of degrees of freedom, order n squared. So when n is large, it's a very big quantum mechanical system. And they are organized into n by n Hermitian traceless matrices. The reason we care about these theories is because they make a lot of appearances in holography. right? Well, this is one reason we care about these theories. For example, two very famous examples are that the C equals 1 theory, string theory, is dual to a double scaling limit of a matrix, matrix quantum mechanics, and the other famous example is M theory or type 2A in BFSS, depending on the, yeah? And another motivation to take this type of approach to this problem is that what we care about is large N. And usually these theories are famously hard, matrix quantum mechanics theories are famously hard to compute anything in. And the usual numerical approach one would take would be Monte Carlo, which is not very good at large N. Yeah, one has to extrapolate. And maybe another motivation is that, for example, BFSS has fermions, so with Monte Carlo you have a sign problem, which is, as far as I understand, usually ignored, but with this approach you don't have any problems with fermions. Now, why finite temperature? Well, as many people mentioned today, we want to understand aspects of black hole thermodynamics, of black hole physics, and that all of that is accessible from finite temperature observables. Maybe another reason is that there are some interesting phase transitions that are predicted for theories of two matrix quantum mechanics, the quantum mechanics of two matrices. There are some interesting phase transitions that have been predicted, and it would be good to see them numerically and find more. So, finite temperature now. KMS states are defined in this way. We all know them. This is kind of the familiar way that we write them. But they can be equivalently defined also by just looking at the observables. This is more kind of a bootstrap way of defining them. We define the observable in this way, and then if all of the observables, so for any O1 and O2, this is satisfied, then this state in which you're evaluating the observable has to be the KMS state. These two lines are completely equivalent to each other. So this is more kind of the bootstrap way of phrasing it, but it's still not usable for us. We're going to take another step. We define these matrices, A, B, and C. The original constraints, before we were talking about finite temperature, were just this A, it's a norm positivity, plus this, it's the equation of motion. And now we add to this big semi-definite positive constraint, which we'll refer to as the thermal positivity constraint. So the thermal positivity constraint, I can explain it relatively easily by taking the large beta limit. So this is the small temperature limit. In the small temperature limit, only the C term survives. And the positivity of the C term, now we're in the large temperature, so we're in the vacuum, right, in the ground state. And what is the C term? It's what happens if we measure the energy after or before a perturbation with some operator. So of course, if we perturb the ground state with an operator, the energy can only go up, right? So that's why at the large temperature, this is just semi-definite positive. Now, if we are going to finite temperature, we're allowed to reduce the energy, but then we have to also reduce the entropy, right? To make the new state less favorable, we have to also reduce the entropy, and this is this big log term. Now, a log we cannot really use in semi-definite programming, but what we can do is we can approximate it from below so that this inequality is still rigorous. We approximate it from below by something linear. So a bit of results. We start with an anharmonic oscillator, which can be thought of as a one-by-one matrix quantum mechanics. We have here better and better approximations for the log, and we see that the bounds kind of start converging towards this black line, which is actual numerical result. Of course, it didn't fully converge because this is level 10 truncation. Like the length of the words are truncated to 10. Now we move on to this one matrix quantum mechanics. This is ungauged. The gauge case at large N is solvable through looking at the density of eigenvalues, but the ungauged case is not solvable. So this is the simplest case that we can test our bootstrap with. And these are bounds that this is the energy or the expectation value of the Hamiltonian as a function of the temperature. And we see the convergence is pretty good. So the green lines are at this length truncation 10. Here we see that the results are good to 3 digits, something like this. There's a log plot, but maybe I won't say more about this. These are again the results from level 10 truncation compared to what we can do analytically, which is large temperature and low temperature expansions. The high temperature expansion is essentially, right, the thermal circle is small, so it's like a zero mode matrix integral. It's no longer matrix quantum mechanics. If we go to the low temperature, there is a more interesting expansion that, because of time, if anyone wants to ask me about it, I would be happy to talk about. But I think it's more non-trivial. It's inspired more or less by Maldasena's long string picture from 2004 paper about C equals 1 string theory. And she and Balthazar and Rodriguez paper from a couple of years ago that also analyzes in the context of C equals 1. This is not in the context of C equals 1, but it's a very similar type of philosophy. The final thing I can show you is...
Sorry, can you go back?
Yeah. Of course.
So what's the blue, the gray, and the yellow are what?
Yeah, sorry. So the yellow are the results from Bootstrap.
Okay.
This is results you can do it at any temperature. The gray is the large temperature expansion. This is from the circle becoming small. The blue is the low temperature expansion. This is you start from, essentially the low temperature expansion is based on, when you go to very small temperatures, you have just the gauge theory, basically contribution, only the singlets contribute. Once you start increasing the temperature, you get contributions from also higher representation.
So why is the bootstrap more converged in the small temperature regime than in the large temperature regime? Because it seems like there's kind of a discrepancy at large temperature, right? Especially in the plot in the bottom left corner.
So sorry, the plot, these two plots, also in this plot you mean?
Yeah.
Okay, the reason is that we cannot push the bootstrap to higher temperatures.
So you think that at sufficiently high temperature they would converge? It's just that you're not at high enough temperature.
The numerical problem becomes harder for the SDP solver to.
Okay, but you do think the bootstrap is converged in the plots you're showing us. You don't think it's going to change. You don't think that yellow line would change too much.
All of this plot. I'm showing you both the lower bound and the upper bound. The orange thing is both the lower bound and the upper bound.
Okay.
So they are right on top of each other. So here I'm just showing you negative G plots, but I guess maybe I shouldn't talk about it too much. Just at some temperature, once you take negative G for anharmonic oscillator, it's an inverted potential. Because of large N, you still have stability at low temperature, but there's some critical temperature where you lose, where things boil off and go out of this little valley. And here you can see some upper bound. These are upper bounds on these critical temperatures. But okay. The last thing I will say, you can also do two matrix quantum mechanics. This is just this very, very preliminary example where we had length truncation 4. So the words are very short that we included in this. It's a very small basis compared to what we should include to get good results. But you already get pretty decent convergence between the lower bound and the upper bound for this plot. So the main point is that based on some notion of positivity, together with equation of motion, we can compute different quantities in these simple observables in these matrix quantum mechanics theories, or numerically but rigorously. We don't have any issues with sign problem or with large N, even though the example I showed you doesn't have a sign problem, but in principle we have no issues with sign problems. And we can do it now at finite temperatures. There's a bit of an over thing. Yeah, okay.
So what are the things you still need to do BFSS?
It's just a bigger problem. It's just a much bigger setup. So people are now working on BFSS. Henry Lin and Zechuan are working on BFSS at zero temperature. There are already challenges corresponding to doing representation theory of the SO9. But in principle, this is just representation theory that is missing there. And once you do it at zero temperature, we can generalize pretty quickly to finite temperature, but the ungauged version of BFSS. Now,
could there be some advantage of doing non-zero temperature? Like, could it be like technically easier by doing non-zero temperature but very high temperature or something? Like could that make the problem somehow simpler?
Well, doing very high temperature, you're reducing to a matrix integral, so that's analytically, not a bootstrap.
Yeah.
But you can do, for example, you could reduce to a matrix integral and then do the bootstrap for the matrix integral, which can be a simplification. I think generally we see that the convergence is better at lower temperatures than at higher temperatures. But one thing that is important is that what we discovered only after starting to think about higher temperatures is that this constraint for 0 temperature even was critical for convergence. So you get much better convergence if you include this, that this is semi-definite positive.
Can you just explain what is the derivation of this condition that you wrote?
Of this condition?
Yes.
I cannot explain. I think I'll need another 15 minutes, but I can explain the intuition.
No.
Okay, so the intuition is that this is variation of energy. This is a perturbation. What you want to do is take your state, act on it with something, and then measure the energy, right? And then compare it to measuring the energy and then acting on it with something. So this measures the perturbation of the energy. This thing measures the perturbation of the entropy. That's a bit harder to to explain. But in principle, this is the role of this thing, and then you want some basically an energy entropy balance. You want to say
Which paper should I read to see a
Oh,
derivation?
sorry, I forgot to mention that these are the relevant papers for this derivation of this. Yeah. There are more papers by Fauzi. All of them are relevant, but these are the most relevant.
There's two people named Fauzi.
There are two people in Fauzi. One of them is on all of the papers. One of them is on a subset of the papers. I don't remember which.
So you say things converge pretty well, and do you have any hope that you can somehow? Do you think things converge really to a point here? And do you have any hope to maybe show that analytically? That's like one of these big questions in the conformal bootstrap.
Right.
Are you in a better situation here?
It seems that it's a bit more immediate. So there are proofs. Minjae and Sun, Cho and Sun, have some proof of convergence properties. This is for the lattice easing bootstrap, which was in this paper. So they have in this new paper they have some proof of that. So it seems like it's possible. We might need to do it on a case by case basis. For matrix quantum mechanics, I don't know that anyone did it, but I think for spin chains there are some results. But the expectation that we have, the intuitive expectation, is that it always converges. So far, in all of the examples we studied.
So as far as I know, in the sequence 1 model, it's still unclear whether you have black holes at all. So can you say anything about it using your results?
Oh, sorry. So I think C equals 1 will be the harder one, actually. BFSS might be the easier one. Because in C equals 1 you have to take this double scaling limit. Now I cannot say anything, of course. In principle, maybe it's a possibility that we can do this because we can do the bootstrap directly at large n. Maybe we can do the bootstrap directly on the double scaling limit, but it's a hard question. So. But for example, in BFSS, if you just repeat the setup, it's the same conceptual ideas, just harder setup. You could, in principle, probe this non-supersymmetric black holes that you're supposed to get already at pretty low temperatures.
Okay, so I guess let's thank Barak again and go to the next speaker.